All right, so part two. So I'm going to take hopefully just this afternoon. Hopefully it doesn't flow into tomorrow morning, but it might. If you're really trying to do reinforcements, then part of it is understanding when a tower shows up as overstressed. What does that mean? What are the calculations that are being done? What are the different ways that a structure can be overstressed? And then what do you need to modify to fix it? And all of that really ties back into engineering strength calculations that are defined in this document, which is ASCE 10, which is the design of lattice steel transmission structures. So everything that we're going to be talking about here this afternoon, and it's going to be equation-based and somewhat technical, is to try to help you understand how the requirements of this document are automatically done within the program, but what the responsibility of the modeler is in making sure that different properties have been input correctly to get the calculations to come out right. Garbage in, garbage out. So if the member is modeled incorrectly, then the strength will be calculated incorrectly, and then you may be reinforcing things or not, don't need it, or not reinforcing things that do. As we proceed, I guess keep these concepts in mind. We want to take advantage of all of PLS Tower's automatic calculations. Therefore, you want to try to input as much information as possible into the model. There's some instances where I've seen that certain connection information is omitted from a model because it's faster to do it that way. But if you do that, you're omitting specific strength calculations, and you're not getting a full picture of the strength of that tower. So one of the things that we really harp on a lot is, all the information that we talk about here this afternoon, we really think need to be in every single model that you're analyzing, or you're not getting a full picture. One of the things that I will touch on somewhat this afternoon is that how much do we sharpen the pencil? In other words, there are some minor approximations that you can make to kind of more quickly model a member. An example might be a complicated bolt pattern. There might be some simple ways to conservatively model that bolt pattern so that you get a slightly conservative rupture calculation, for instance. But the speed that you would get in making these simplifications might be worth having a more simplified and conservative model. But I'll also say, is that if it's too simple and too conservative, then what you may find is that you're having to really refine the model after you run an analysis and find overstresses. So I've got some examples where I'll try to highlight ways that you can kind of, I don't say take shortcuts, but make some simplifications in your modeling decisions that can save time, and it's not going to create a dramatic conservatism in the calculation of the member strength. You should have a sheet like this at your table. You're really not going to use this as we talk today, but what I like about this is that this is basically every variable that PLS Tower uses in calculating the strength of all the limit states that it checks. And so the variables are listed as you would actually find them in the Tower manual. There's a general description. The input location is where you actually will find that property physically input into the tower model. So like the first three are things we've already looked at: steel material properties, the angle properties, and the bolt properties. What we're really going to be focusing on a lot this afternoon is the member connectivity, so that members table. And then PLS Tower is checking 6 limit states for you, and they're listed across the top. There is net section, rupture, and block shear. Those are tension limit states. Bearing and bolt shear are tension and compression limit states. And then buckling, or L over R, is a compression limit state. So what we're really going to focus on here this afternoon is talking about those 6 limit states, the calculations that the code requires, and how you get PLS Tower to do those calculations for you in the most accurate way possible. Okay. So I'm basically just going to start going through one by one the 6 limit states that we've kind of talked about. The first one we're going to talk about is a tension limit state, and it is basically, Tower calls it net section. Essentially, any member, and a net section of a failure is, what is the tension capacity of my member through holes? So, right, I can see that this member broke right through this hole on the end of the member. So the area that was subjected to the tension wasn't the full gross area, it was a reduced area, it was a net area, some measure of net area. And the code requires that we basically analyze across that net area some design tensile stress. Now, the easy answer is that the design tensile stress is generally the yield strength. So it's basically the yield strength on the net area. But there is a provision that says that you have to reduce your tensile strength to 90% of the yield strength for members that are connected on one leg. So like in this case, if this was a tower, this angle, when I would calculate the net section capacity, I would have to calculate the area minus one hole, and I would say that 90% of the yield strength is what is allowed on that area. That's the design tension capacity of that area.
What's the reason for the 90?
Great question. So the 0.9 reduction is to account for something that's called shear lag. Okay. Generally, if you look at the figure, if I have an angle that's connected only on one leg, then really at the connection where I'm transferring all that load is transferred through the bolts. And so, at that, bolt location, it's probably not appropriate to assume that you're loading the full cross section in tension. Okay? AISC actually has more very laid out provisions for how to account for shear lag, and it's based off of the length of the connection, whether it's bolts or welds and all that kind of stuff. Essentially, in tower, the simplified approach is, if I've got a member connected on one leg, I'm going to reduce my tension stress, but really what I'm doing is I'm accounting for the fact that I'm not able to apply the full yield stress over the entire section. And one of the things that I'm going to continue to come back to is, and it's worth mentioning now, this document started as like a manual of practice. So like the ASCE 113 for substations is a manual of practice. It is a best practices guide. It's not a standard. Essentially, everybody in the industry got together and said, how do we want to design towers? What are you doing? What are you doing? What am I doing? Can we come up with a list of best practices? And that guide was out for a number of years, and then they kind of formalized it into a standard. And to formalize something into a standard, you have to make sure that you have equal representation from all parties involved, vendors, material people, engineers, those kinds of things. So, but eventually, I'd say 90% of what was in that manual of practice has come into this standard. Where I'm going with this is, a lot of the assumptions for limit state checks are things that have just been around for a long time, and there's simplifications that have been proven with successful use. And so, what you're going to find a lot of times is the equations here may not be as thorough or as extensive as you see in the steel manual, but it's worked for the tower industry very well.
That section's always going to be at a joint where the bolt.
It's going to be where you have holes, yes. Yeah. Absolutely. Now,
it's always going to be your weak link location, right?
But it may not be at the end of the member.
Oh, yeah.
It may be somewhere else.
Yeah.
But you're right. So part of where this can get complicated is the net area is nothing more than the gross area minus the loss due to holes or other openings. And I've already talked about if the hole is punched, you have to subtract 1/8 of an inch greater than the hole diameter. One of the questions that we have to answer, though, is I basically have, in this particular connection, I have 2 different potential failure paths. So I could fail right through this one hole, or I could fail on a staggered pattern through 2 holes. So I maybe have more reduction but my path is longer, right? So there's no guarantee which one is critical just by looking at it, right? There are methods for how to account for that. So what the standard tells us, and this is pretty consistent between the tau ASCE and AISC, is that essentially for staggered patterns, you subtract the total number of holes and then add back this value of s squared over 4g. What does that mean? S is essentially the spacing between holes, and g is what we call the gauge between holes. So if I were to evaluate this failure plane, it would be the gross area minus the area of one hole. If I were to evaluate this failure plane, it's the gross area minus the area of two holes plus s squared over 4g. This is empirical. I think it was developed not by the tower folks, but by the AISC folks. And so, at some extreme levels, it can break down a little bit. But generally, it is the approach that's consistent in all steel design in the United States. Okay, and this is exactly what I just explained. So, two different failure planes. I will remind you that you're going to see this value h a lot. H is hole diameter. I'm used to seeing d sub h. But within the tower code, they define that as h. So h is the hole diameter. So gross area minus one hole diameter times thickness, or two holes times thickness plus the s squared over 4g.
So there's a second failure. Does the second one usually control? Is that usually
It's going to depend on, essentially, the more these two holes are aligned, the more that they control. But if you get some pretty wide staggers, then potentially the first one controls. Okay. Click. There.
PLS doesn't do this for you, does it?
You have to figure out which one. That's right. This is one of the things that PLS requires a lot of pre-engineering work to get done correctly. This is one of the more difficult ones to do.
This is the area where we had a lot of issues on models that you guys checked for us, I guess, right?
Yeah. One more rule. PLS does do this automatically. If you connect on a short leg, then the gross area is considered to be only the length of the short leg on the non-connected leg. So if this was like a 3x5, then the gross area would be assumed as a 3x3. And again, this is kind of one of these rules tied to the shear lag issue that was a best practice that's been around for a long time and has served us very well and successfully. This doesn't come up a lot, but this is an automatic thing that is done within Tower. So you don't need to worry about this because we specify whether it's connected on the long or short leg. And so then if it's connected on the short leg, it will do this automatically.
It still takes the 90% of that.
That's correct.
Too.
That's correct.
So, why would you design it with a long, if you've been doing that forever, why would you design it so it's attached to the shorter end? Where does the longer leg kind of come into play now?
That is a good question. Where that would come into play would be if I'm looking at a tower body and I've got this long horizontal member that connects to the leg diagonals. One of the things that I may realize is that in the plane of the screen, this thing is braced at this point. So its buckled shape, so it comes into play in compression. Its buckled shape is going to be something like that. It's going to be braced out of plane. In and out of the page, if I don't have a diaphragm there, then its buckled shape is going to be essentially the full length, right? And the whole thing's going to buckle in and out of the page. So if I have an unequal leg angle and I orient it such that such that the long leg is basically horizontal, then I'm putting the stronger bending axis in the direction of the longer unbraced length, so it can create a more balanced design. And so that's a situation where it's going to be connected on the short leg. So when you're looking at a net section, you're going to have to look at it with the reduction, but there's benefits in buckling. Other considerations, clips and blocks. So this doesn't come into play a lot, but when you look at details, a number of times, if you're trying to get all the members to fit together, you might have to cut the outstanding leg. So there's basically this detail says that the outstanding leg needs to be cut 2.5 inches from the end. So it's basically nothing more than a flat bar on the last 2.5 inches. And my hole is only 1 inch from the end. So my net section is really only one leg of that member. All right, I've basically got the same example here. So 2 different examples. Go back.
So that's something that you have to kind of do manually.
You're going to have to manually input that as well. So the staggered bolts and something like this are things you're going to have to manually catch. I've got some equations to kind of show you how to do that. Okay, go ahead. Right, so Tower provides automatic calculations. It can be very helpful for simple connections. For more complicated connections, you've got to do some of the work to get the input. So the FY, the 90% reduction when you're connected on only one leg, long or short, is automatically applied. And the area reduction when the short leg is connected is automatically applied. Okay, so it does do that for you. What it doesn't do automatically is account for these staggered bolt patterns. It doesn't account for these blockouts or these clips on the outstanding leg. And it doesn't consider whether the critical section for net section is in the middle of the member versus the end of the member. Right? These are all decisions that we have to figure out, that we have to adjust our input to get it to calculate the proper net section. Okay? So how do we control this? So we're looking essentially at the member connectivity table. And it's truncated. I'm only kind of showing you the pieces that matter. For the net section calculation, what matters is the connected leg, for reasons we've discussed, and the number of holes to remove from the section. Now, for the issues that I talked about with staggered bolts or the clips and those kinds of things, what ends up happening is how this works is that we have to input a non-integer value for the number of holes to kind of get the program to calculate what we want. And I've got some examples to show you exactly how this works. But like the idea generally is if I have a tower, if I have an angle with a staggered bolt pattern, what Tower does in their equation is they basically say that the net area is the gross area minus the number of holes times the thickness times the diameter of the hole. So the only real input that you have to this equation for net area is number of holes. But we know that if it's staggered, the actual equation is the number of holes plus this s squared over 4g calculation.
It's always assuming that they're in line.
It always assumes when you say number of holes, what Tower is going to do is it's going to look at that. And what you have to do is you have to tell it, well, my equivalent number of holes to take out is going to be 1.5, 2.25, right? So that what it actually calculates as the net area is the calculation you want, whether it's a stagger, whether it's the outstanding leg is clipped. You've got to kind of figure out what these numbers are. In almost all towers, these things are going to be non-integer numbers. Only the simplest towers where you have a single row of bolts are these going to be integer numbers most of the time. Okay?
So how do you, well, you're going to get to how you account for the clip?
Yeah. Yep. Okay. Other thing to think about is I'm looking at this leg member here. So basically, here's the splice that occurs down here, and then this horizontal is this guy. So it's kind of compressed. This redundant member is this guy right here. So a lot of times, some of the issues that we see with tower models is that the modeler will only consider the bolts in the connection for specifying the number of holes to remove for net section calculations. However, if I look at this and I look at the stagger here, these two bolts are on the same gauge line, right? The gauge is 1 5/8 inch, but the spacing of these two bolts is 2.5 inches, and the spacing of these two bolts is 5/16. So clearly my diagonal is less here. This is almost nearly 4 complete holes. There's a small stagger. So this is my weak point, right? So when I calculate net section, I want to calculate it for that location. Make sense? Okay. So in your, I handed out some hand calcs, and I'm going to open one of those now.
It's the last one.
It might be the last one in your packet. Basically, the top says calculation equation of equivalent number of holes for PLS tower. So I'm actually going to kind of go through the derivation of the equations to calculate this non-integer number, right? How do you do it? So I'll let everybody kind of get there. All right. So basically what I'm showing here is I'm going to derive this equation. And what we're looking at is very similar to what I've drawn. I've got, in this case, a staggered bolt pattern. And I want to investigate 2 different potential failure planes. So 1-1 is straight through one hole, and 2-2 is along this staggered pattern. I got to check them both. Recall, right, that the tower equation, the equation in tower for net area, is the gross area minus the hole diameter times the thickness times what I'm calling here is n sub h tower, the number of holes that you input into tower, right? This is the equation that tower uses. What I need to do is I need to figure out what the appropriate equations to calculate the net area for both of these failure planes and set them equal to this equation and back solve for number of holes for the tower. So if I look at failure plane 1, 1, I know that my net area is the gross area minus the hole diameter times the thickness. There's one hole I'm taking out. All right. For section 2, 2, it's the gross area minus 2 holes, 2 times the hole diameter times the thickness, plus this s squared over 4g, and then both of those have to have a thickness multiplied it because the s squared over 4g is a length. So there's a thickness that's multiplied by that term. Okay? I can basically set the equation 1 and equation 2 together equal, and equation 1 and equation 3, which I've done here and here, and you back solve for number of holes in tower in both of them. And what I find is that for section 1, 1 through one hole, the number of holes I would put into tower is 1. Let's call that an obvious solution. I'm subtracting 1 hole on the gross area. If I'm doing the stagger, it's essentially, if you solve through, it's 2 minus this s squared over 4g times the hole diameter. Right? That's how if I reduce this and solve for number of holes in towers, this is my equation. So if this number is less than 1, then 1 controls. If it's greater than 1, then the stagger controls. I can repeat this calculation for 2 staggers. right? So you can have patterns that have a hole pattern like this, where I potentially have to stagger twice as I go through, right? And I can follow the same procedure. The actual net area is the gross area minus 3 holes, and then basically if my minuses will cancel, I'm adding in 2 times the s squared over 4g. So we'll assume that these 2 g's are equal. I know my figure doesn't show that, but we're assuming those 2 g's are equal. And then I get basically that the number of holes I have to put in tower is 3 minus 2s squared over 4gh. Okay. If I have a variable number of staggers for 3 staggers, 4 staggers, 5 staggers, the number of holes I put into tower is the number of staggers plus 1 minus the number of staggers times s squared over 4gh. So this is your general equation. Right? That's how you can back calculate the number of holes in tower.
It's all based off of like a perpendicular of the like dimensions from the leg or the angle.
Yeah, I mean, you're talking about S and G?
Yeah.
Yeah, and essentially what I'm saying is that if I calculate this number, I put this number into tower, the net section that falls out will be equivalent to the real equation. If I were to do the real equation with the staggers, that I would get the net area that falls out of that is equivalent.
Yeah. So is this something that typically most people are doing, or is this something that you got? I know you guys do it.
I would say that one of the ways that you can quickly bypass this is in the example that I show, where you basically have 2 holes that are staggered but pretty close. Then if you've got 2 on this face and 2 on this face, you take out 4 holes, instead of worrying about the little stagger where your answer might be 3.9.
Yeah, I'm just saying, are most
I don't know.
firms doing this kind of
I don't know. I mean, my thought is that there are, if the number is close to an integer, like if it's 3.9, then we talk about this idea of fast, simple models. You can very quickly not do this, and you can make a conservative jump and say, well, there's 4 holes I'm going to take out. If you have a net section problem, do you reinforce, do you replace the member, or do you come back and do this? And if you have 15 net section problems, then would it have been better to just model it right the first time and not have an overstress show up in every single tower model that you create, right?
How often does this become the controlling factor? Does that vary a lot? Or?
It depends. I mean, I've seen in legs it happens a lot, because these net sections that I showed, like the one in mid-member, a lot of times you'll find that those can become critical, because you might have 3 bolts connect on a leg, so you have up to 6 bolts that are being taken out. And when you evaluate these old towers, you find that it doesn't have the net section strength in those places. So in legs more than maybe others, usually it shows up where you have like in legs, like I said, you might have areas where you have lots of bolts. In bracings and stuff, you got one bolt typically, so
have
it's not.
Have you guys ever talked to PLS about this and incorporating this kind of stuff in?
I mean, they're continuously updating their connection view. I think that they specifically will tell you sometimes you need to put non-integer values in. Like, they'll tell you that.
Okay.
And I feel like this is something that we commonly do see in models that we do peer review for others, is that this kind of thing is captured.
Okay. So you see others doing this.
Yes. Yeah. I think this is a pretty standard thing.
But they don't have anything, or you haven't heard that they're building anything into PLS to do some of this.
No, and I think a lot of it is because there's already a lot of variables. Connection modeling is already difficult, and if you really get into trying to specifically lay out exactly where the holes are, it's really going to up modeling time tremendously. Where, stuff like this, you've got the equations. It's pretty easy to build a very simple spreadsheet. What's the hole size? What are your gauges and your spacings? And you can figure that stuff out pretty quickly. And that's what we do. I mean, we have stuff that you just input it in, and it tells you the equivalent number to put in.
Like you said, I mean, it's pretty difficult to do it for all of multiple members, but at the same time, how many members are looked at everybody looking at the different boards? So the different connections on towers. Do you look at, like, for example, the legs that you probably have 6 bolts?
We do this for every member.
For every
Now, again, if you have a diagonal member, that has hole patterns like that, this is an easy calculation. It's 1, right? A lot of times these things might be off slightly, but it's only to fit the bolts in. But you can look at this and see that the stagger is so dramatic that it's 1, right? So really, a lot of times it's leg modeling, or as you get higher in voltages and you get the more bolts you have in a connection, the more of a nightmare this becomes. So the higher voltage towers become more difficult to do. But we look at it for every member, and there are definitely diagonals that overstress in that section. For when you look at it like this.
Yeah, back to the question on will PLS incorporate this? They're continually improving it, and just like we'll get to the block shear, the shear tension pads. It used to not have those columns in the
right.
tube, so we used to have to fudge something to
right.
get it to work, and now they have simpler.
Yeah, so they're always looking to improve. I think their main driver is demand. If you had a lot of people complaining about it, they'd address it. If it's 1 or 2 people, they don't.
Yeah.
That's just how they operate.
I mean, if you can, I know you kind of looked at our models before, and if you can just kind of point out which areas were the biggest areas of concern in our models. That maybe varied a little bit, but.
So for me, the biggest comment was, we say connections aren't modeled. And that's when you get, and we'll get there, when we talk about the rupture limit states. When you're not inputting gauge lines, you're not inputting spacings, you're not putting in block shear values, you're omitting all of these kind of end rupture limit states. Most every model I've seen has some value in for these net section. It's very common I see non-integer values. Like you don't typically see something where they're all straight integer values. And so from that perspective, this is not necessarily a huge deficit, but
yeah, as you go to the other items.
Yeah, I will.
If certain ones are
absolutely
key ones that you've seen issues on, just let us know. So
because
now it makes a heck of a lot more sense after going through all this now than what we were talking about years ago.
I think one of the comments we had before was that the hole diameters were not 1/8 of an inch larger; they were 1/16 of an inch larger. Well, that permeates this because that impacts this value. I mean, it comes up in a lot of places. So there's different small things in different places.
Yeah, okay.
So how do you account for a clip? So you can, in this case, I'm actually showing an actual clip as opposed to a block out. But if you can calculate or approximate essentially the length of material missing, then you can take the you take the previous calculation and the number of holes per tower that comes out of that, and then you basically add this value to it. So in other words, the number of holes equivalent to this clip is the length of the clip divided by h, which is the diameter of your hole. So if I know that this is 2 inches and I have a 3/4 inch diameter hole, then essentially I'm missing 2 inch divided by, what is it? That's a terrible example, but if I have a 1 inch diameter hole, I have 2 other holes down here I'm missing. So I can do my previous calculation and then I can add 2 holes to it. So not tremendously difficult, but again, another step. We don't find this very often because most of the time, if a member is clipped, so I'll look at something where I've got my member and maybe I've got 3 holes or something, and this is clipped here. So by the clip, I mean if I look at it in the other view, it might look like this, so where my holes are here. Well, we always assume that the net section is going to occur where the member sees the full load. So you're never going to have a net section through here because it can't break away. It's got to break away on the end bolts. So if I look at, this section, I don't have to worry about the clip. So it's a very, it's we see it sometimes,
Yeah.
but it's not a common thing.
What's probably more common is that full clip.
Right. That's right. But a lot of those are on redundants. I mean, that's not a tremendous issue, but it's something to be aware of.
Is that why you are not accounting for the other bolt?
That's correct. That's right, because the idea is, let's say that this has got 20 kips in it. You assume that you got 10 kips in each bolt. So if I got 10 kips in this bolt, then this section sees 10 kips and this section sees 20. To really fine-tune, sharpen your pencils, maybe I should check this for 10 kips and this for 20. But in my mind is that what I'm really concerned about is the member snapping in half and no longer being connected. Whereas if I started to lose some strength here, maybe it transfers some strength to the other bolt. Like, I'm mostly concerned with at the end of the connection where it sees the full tension. That's what I would call state of practice. That's what we do. I've not seen anybody that does anything more specific than that.
You've never seen an actual failure occur.
Oh, right. That's right. That's right. Yeah.
This, I guess the extent of the connection analysis
He's got a lot.
Oh, no, there's a lot more. Get ready. We got 4 hours of it. The other thing, again, this is a very rare consideration. But if you have a member where your critical net section is mid-member, like we've showed for the legs, but the member is only connected on one leg, so not a leg member. Maybe like an arm on a tower, right? The arm is connected on one leg, but then maybe I've got a bunch of holes in the middle to connect to a bunch of bracing or something. So because you are telling the program it's connected on one leg, it's going to be using the 0.9 FY in the net section calculation. But if you're in the middle of the member, you can kind of assume the full cross section has been engaged. So you can actually adjust the number of holes, right? My desired calc is use the full FY times the calculated number of holes. What Tower's really doing is it's using 0.9, and so I want to calculate an adjusted number of holes such that these two things are equal, right? So my final adjusted number of holes is this equation, which is, again, based off of the calculated number of holes in a tower. This is very rarely done. This is very, very rarely done. But at times, you may have something that's only overstressed in that section. And if you look at it and say, well, I'm saying there's two holes in the middle of the member, but it's connected on one leg, then Tower's actually it's over conservative because it's applying not the full yield strength to that section. And you can kind of back off the number of holes and get a more refined analysis. I mean, you can do a hand calculation too, but you can get Tower to do the calculation this way. So, and the only difference is this calculation requires knowledge about the angle. So you notice there's actually the thickness and gross angle area in this calculation that doesn't exist in any of the others. That's one of the only differences. So I provided an example. I'm going to look at the same thing that I looked at before. This is this leg member. We're going to calculate the net section for that member. And so I've highlighted the member here in the drawings. We're going to be looking at the mid bolts here that I keep pointing and it moves. This net section, I've highlighted the gauge is 1 5/8 inch. The spacing is 5/16 of an inch. Okay? So my spacing is 5/16. My gauge is 1 5/8. We're going to assume 5-inch bolts, so my hole diameter is 1/8 of an inch more than that, 1 3/4. My number of staggers is 1. I've got 1 stagger here. And then one of the things I'm adding is the number of legs. I'm talking angle legs, right? I've got this stagger on this leg and I have a symmetrical bracing in the perpendicular direction. So I basically have up to 4 holes here. So the number of legs. So I can take the general equation that I provided before, and I'm just going to basically double it because I'm going to multiply it by the number of legs. So the number of staggers plus 1, and then I plug in everything else into this equation. The number of staggers, the S, the G, the H, if I do all of that, what spills out of that is 3.96 holes. You could have just put 4. And does that make sense? Absolutely, because these 2 holes are almost perfectly aligned. If they were perfectly aligned and my stagger was 0, then this whole thing turns into 4.
So
right?
Backing up a second, I mean, obviously looking at this is pretty complicated. A lot of connections on this.
Yeah.
Is that just kind of visual, just looking at it and saying, okay, I got 2 holes in there, the most in line.
Yeah.
So those are the most critical ones.
Pretty much.
You kind of came to that.
Yeah, so I mean, when I look at this member, what do I see? I see, first off, we're looking at, here's the member. It continues up, but I've modeled it from here to here. The piece I'm looking at that I modeled. So I want to calculate the appropriate number of holes for that particular segment of leg. And I'm basically looking at the spacing, right? This one is 2.5 for each bolt. This is 1 11/16. Again, these things aren't drawn to scale. You actually have to read numbers. This one's 1 5/8, right? This one's 5/16. So this one's pretty obvious that you can look through and say, this is the critical path. That's not always the case. Sometimes you have to run the calcs for a couple of different scenarios and find the worst case. So, but yeah, I mean here, the answer is, I probably would have modeled this as 4. I would have sent it to Greg for review. He would have come back and said 3.96. We would have fought about it. We would have argued about how much you need to sharpen the pencil. But as you do this, you're going to kind of learn that you're going to be able to see if they're almost in line, then you're going to get a feel for the fact that the total number of holes is almost 4 anyway. But sometimes that's not the case.
And a lot of times you may be in a groove, just calculating a bunch.
Right.
And so you're gonna end up calculating this one where if you
Right.
were gonna find the ones where you weren't gonna calculate first. Then
And here's another example. So I'm looking at this leg member here, along this leg. And now it's not particularly clear. I don't have a situation like this, right? Here's 2 1/16. These are 2 so this bolt and this bolt are 2.5 inches apart, and this one are 2 1/16. Then it's not drawn to scale. You got to be careful about that. But then I come up here and I'm looking at 1 11/16, 2 1/16, 2 3/4, 1.5. So here's probably the critical one right here. So something through that path, because these 2 bolts are only 1.5 inches apart. So you can find that. Usually you can figure out which one to do pretty quickly. It becomes more complicated when you have 3 gauge lines and you might have 3 holes you have to look at. Then it gets to be a little pain in the butt.
So is anybody doing this stuff graphically? I guess other than new towers that they hopefully are designing at 3D CAD and stuff like that.
Right.
Yes.
If I'm designing this new, I'm saying 4 bolts in my model. I'm sizing the member so that it can handle 4 bolts. But then if I'm the designer and I send it out for detailing and it comes back and the detailer has put 3 bolts in a connection here, and I think I got to look at net section, maybe I got to update. I mean, that's part of, if you're hiring somebody to design a tower, that's part of what they're doing. They've got to verify that the details match their assumptions.
Have you guys ever had discussions with actual tower design people that are designing new towers or have designed these old towers, and is all of this detail typically been looked at in the design?
I would say that the limit states that are in our code today weren't all checked historically. There is something, the appendix of this document actually recognizes that and even says it's not reasonable to expect every old tower to pass every provision of this code. And then it says that it's kind of okay to accept mild overstress if you have 30 years of successful behavior from the structure, if you have old test results you can look at. They allow you to engineer judgment away 5-10% overstresses. Now, if you do decide to go do something, then you have to meet the standard. So if you're going to design a new piece, it has to meet the new standard. But they do allow you to fudge away, and like for you guys, when we did Fractal Columbia, we had some discussions, but all of your load cases had the 1.25 factor on them. So the loads that were controlling these were above legislated loads. There was, not the NESC loads that were controlling it. So one of the options when you're looking at these old towers, especially if you're evaluating them under the old load cases, is are you willing to back off that load factor to 1.2 or something else? And if it passes, then you're comfortable, right? But that's a risk decision that ultimately has to come from the owner.
Yeah.
We can kind of help define it for you, but we can't make those decisions.
I know we included something like that in the substation criteria.
Mhm. Right, like a legacy structure versus
For
yeah.
structures.
Yeah.
I've recently worked on that. Might be,
and a lot of that decision comes down to is it a leg member? Is it a critical load carrying diagonal? Is it a tension only diagonal? Are you willing to live with a 5% overstress and a tension only potentially? Especially if you're looking at a wind velocity that's more than code or a 1.5 inch ice or whatever. Those are kind of the decisions that have to kind of be made.
I think it's unfair to go look at the older structures. I think that they are supposed to abide by today's.
At the end of this whole presentation, we'll address that, and like I said, the people that put this document out recognize that too, and so they say you don't have to do this. But the other way to think about it is that the standards in here are best practice, best knowledge today on how to calculate these capacities, right? And so, I know when we get to the rupture limit states, these are things they didn't look at 40, 50 years ago. But there are ways that are recognized that fail these members. And so, if you do show that you're under strength because of that, the decision is, are you willing to live with that risk? Because the capacity is a real thing, even though it wasn't necessarily considered 40 years ago. So as a summary for net section, very common for the number of holes to be a non-integer value, only way to account for staggered holes and clips. For legs, for tower legs, the critical net section is usually usually B at the splice connection. Check for locations where holes are more closely spaced together. Thanks, Chris. All right, so I'm going to move on to bearing. This one's not nearly as complicated. This one's pretty simple. So a bearing failure is we're talking about a bearing failure in the base material. Essentially, the ASCE 10 equation is the rupture strength times the bearing area times a factor of 1.5. Again, this is a little bit different than what AISC does. This is what has kind of fallen out of their recommendations over the years. So you're looking at the ultimate tensile strength of the angle or the bolt. So you could have a bearing failure in your bolt as well, but most of the time it's in the angle. The bearing area is the diameter of the bolt times the thickness times the number of bearing areas, right? So in this case, if this was a connection, you would actually assume even though you see that the failure doesn't happen uniformly, the calculation procedure says I have 4 bearing. If I had 4 bolts, I had 4 bearing areas, right? Times the diameter of the bolt times the thickness. Right. Yeah.
This bearing strength is it always kind of considered tension along the length of the
or compression? Yeah, I load in the other way, it all bears in the other direction.
So it's
this. Oh, go ahead.
I'm kind of confused as to what the heck this really is compared to other things. I mean, this is basically saying it's going to start to elongate the holes.
That's right. You're going to have something that looks like this.
Snap it versus breaking the.
That's right. So it's not necessarily that the member's going to break. This might be a precursor to that, but you're basically ovalizing the hole. I mean, you're failing locally in this connection. Is it as catastrophic as some of the other things? No. But do you really want this to happen to your towers?
Is that
No.
common though that happens versus it breaking?
I'm trying to think. I don't think I see many analyses where the calculated bearing capacity is the controlling limit state.
I don't think so.
I mean, you're really worried about thin angles, really,
Yeah, or maybe soft steel, like maybe.
Right. So generally, like I said, this is a check that's done. This is the requirements of today. But would I say that this is something that generally controls connections? No.
Well, I don't understand, like you're saying, ultimate tensile strengths of angle or bolt. I mean, the bolt is being checked by the shear strength of the bolt. How does the bolt play into, how are you checking the bearing strength of the bolt?
So you could have essentially like a notched bearing failure on the bolt, right? Is that if this is my bolt and I have an angle and there's this bearing surface, is that, potentially if the bolt is shearing, the bolt is pushing against this angle, it might actually have a bearing failure here before the member does, right? That's what you're talking about?
Yeah, that, man, with the hardness of bolts, that's
Now,
almost hard to believe. Okay, yeah.
That's right. Now, again, what I'm talking about here is the bolt can be a limiting value for like A572 steel of today. I would say generally people aren't worried about the bearing of the bolt. And like I said, again, this is not a limit state that's typically controlling. But this is the code required calculation. The only thing that you use is the number of bolts. So you're going to specify the number of the bolts in the connection, and PLS has all the other information it needs. So there's no modification or anything. You just input the number of bolts. It's going to calculate the bearing capacity for you. Bolt shear. This is another one that's not very difficult. The bolt shear is nothing more than the design shear capacity of the bolt times the number of bolts times the number of shear planes per bolt. 95% of the time, the number of shear planes is 1. You've got two different angles pulling in opposite directions that create one shear plane. We talked about the double angle example where you might have 2 shear planes. You have the ability to put that in. I'll show you. But that's essentially the calc that's done. Shear capacity was discussed in an earlier section, and the number of shear planes depends on connection geometry and whether a bolt is in single shear or double shear. So really this one is more about your bolt table. What do you specify as the shear capacity of the bolt than it does about how you actually model the member.
What you were saying before is pretty much use the thread.
Use the thread, use the weak.
Other than that 500 tower that uses those special.
That's right. That's right. So, again, you're going to input the number of bolts and you're going to input the number of shear planes. So in any particular connection, I can say there's 12 bolts and it's in single shear or double shear. So this is how you influence the shear capacity calculation. And if you have a member that's specified as a double angle and you say 1 shear plane, tower will throw a warning and say, hey, you've got a double angle, but you've only got 1 shear plane. Did you mean to do that? There's cases where you might, but it'll say, hey, bring your attention. Warning, 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 warning. So this one, again, pretty simple to calculate. You don't need to do anything special. Just get the number of bolts right. And like I said, make sure if you get something that you have bolt shear problems, make sure your number of shear planes are right. Here's an example of, and I think I showed this one earlier, the highlighted member is a double angle. So I can tell that for a couple of ways. You see 2 L's, 3 by 3 by 3/16. So it's a double angle, 3 by 3 by 3/16. And the other is that you see that there's these stitch bolts. So they actually, double angles will be bolted together along their length. We call them stitch bolts. And you can see that they're detailed here. So, yeah.
I guess that dotted thing is there's usually a washer between each one.
1/4 inch, yep, 1/4 inch fill washer. So a lot of times that'll stand out very quickly as far as whether it's a double angle or not. And when you look at the bill of materials, when you look at the design table, there's a lot of places where it lists the angles. You'll see this 2 L's, double angle. So in this case, these 2 bolts would need to be entered as 2 shear planes. And so you take the shear strength of that bolt, multiply by 4, and that's the shear strength connection of that. So pretty straightforward. I'm just gonna. This is just beating you over the head. Most common error in modeling bolt shear is the bolt shear strength. Bolts have gotten stronger over the years. Modeling a bolt of today in a tower built 50 years ago will overestimate shear capacity. So be highly aware of that. That's always a comment that we have when we peer review, is bolt strengths don't seem to be appropriate. And the general mistake is to make them too strong, so you're not identifying problems.
You guys want to take a break now, or do you want to cover this?
What's next? Oh, yeah, hold on. Just keep going through. So, yeah. So what I did was I recopied in this presentation the bolt strengths for the different era bolts, just so that you had that reference next to that discussion. All right, yeah, we should take a break. All right, so I'm gonna dive into what might be the most frustrating part of our 2 days, which is rupture strength or tear out strength. A couple of caveats as we begin. I don't know this for a fact, but my general assumption is that PLS had a check for rupture, which is kind of this combination of tear out. So the idea of, this bolt could actually tear out of the back of the member, or if the bolts are too closely spaced, you could actually tear out the little section between the bolts. And they called that rupture. And I don't know this for sure. I'd have to go back and look. At some point, they added this failure that we're going to talk about separately called block shear. But they lumped that in their program, probably because their architecture was set up that way. I don't know this for sure. They lumped that into the rupture calc. So their rupture calc, as they call it, is a catch-all that includes a separate limit state of block shear. For our discussions, we're going to separate what I call rupture and block shear. But within the program, it's only going to give you one rupture strength. And that strength is the result of essentially two different calculations. So I'm going to start with what I'm calling rupture strength. ASCE 10, this document, does not tell you how to calculate rupture strength. What it does instead is it says, we're going to give you guidelines for minimum end distances, minimum edge distances, minimum spacings, and that if you meet them when you design towers, then rupture won't be a concern for you. So that's kind of a pain in the butt when you're actually trying to calculate a rupture capacity, because they don't tell you exactly how to do it. For the purposes of our conversation, we're going to talk about three different variables. We're going to talk about the end distance E, which is this distance to the end of the member of the last bolt. The edge distance F, which is the distance to the closest member to the edge. And the spacing in the line of force. So from here to here. So I have a note that says that S, as defined by these folks, is different than the S that we talked about when we talked about the S squared over 4G and the staggered bolts. So when you're doing net section, and I say S squared over 4G, I'm talking about that S. For the purpose of tear out, what we're worried about is essentially the material tearing out in between two bolts in the line of force. So if the force is pulling this way, then we're worried about that distance. And unfortunately, in tower, when they say S, this is what they're talking about in the tower program. There's nowhere in the tower program that they worry about this value. This is what we have to do on the outside. So it's just a clarification to try to save some confusion. Okay?
Is it those dimensions are to the center of the hole or to the edge of the
Center of the hole. Yep, hole diameter it knows the diameter of the hole, so it can account for all of that.
Okay.
This is what I would say is the one piece of tower modeling that's most omitted because it takes the most time to do. And it is basically filling out all of this information. We're talking about the connected leg. It could be the long leg, the short leg, both legs. Most of the time that's input. But then we've got the end distance, the E value, the bolt spacing,